Uh, Sanjeev, could you please confirm if I'm audible?
Yes, sir. Audible, sir.
Okay, fine. So let's start with this week's session, and maybe we'll revise the previous week till someone else joins. Otherwise, we'll start with this week's question directly. So welcome to the live session for week 3 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad, and I am Anant Singhal, a PhD student from IIT Jodhpur. I'll be assisting you in solving similar assignment problems, which is related to week 3 assignment, uh, that will help you in solving the assignment that is given to you this year. So in the previous week we have already covered. So this is the course outline. So in the previous week we have already covered some of the basic topics such as the carrier density, the Fermi levels, how they are made, the what are donor and acceptor impurities. Then we have also determined where are the Fermi levels present in the extrinsic semiconductor, that is near to the conduction band or near to the valence band. Then we have covered some of these topics also. So this week particularly we have some of the more important topics that are related to again the motion of carriers, such as how does the electron move if we apply a certain electric field, how does a electron move, what is the mobility of the electron. Mobility is nothing but the movement of electron. What is the measure of current? So there can be two types of current measures. One is a drift part, one is a diffusion part. So we'll cover some of the questions related to this, and at last we'll be covering for a general expression of power of the current, which will include both drift and diffusion carriers. And at the last, we will see some of the energy bands which are formed under some of the applied electric fields. So this is a very important topics. I should say that this is a very important week. If you get to know about these concepts clearly, then there will be no problem in solving for rest of the topics, because they only involve some of the different types of dopings. We just need to worry about the movement of carriers, how they move. Either they are doing diffusion or either they are doing drift. So if I quickly summarize last week, maybe so we have covered all the aspect, like the Schrodinger equation, how it gives the density of states, which is nothing but the solution of Schrodinger equation is the density of states. Then we arrived to the relation for the carriers. So we had four relation for n type. We had uh, like two relations, which is related to the effective density of states, which is this NCA, and exponential of the difference between the conduction band and the Fermi level over kT, which is in electron volts. Then we had similarly we had for the p type, which is the effective density of valence band, and the relation remains the same, which is EV minus EF over kT. Then with respect to the intrinsic level, we saw that we had certain relation n will be computed with respect to the Fermi level, that is EF minus EI over kT. And at last we had for P, we had the intrinsic level exponential of EI minus EF over KT. So what it symbolizes for all the degenerate, or sorry, not degenerate but non-degenerate semiconductors is that NC is always less than P. Here we can clearly see that NV is always greater than P. Here we can see NC is always greater than N, and similarly Ni is always less than N. So you can clearly see how I made this, because if this exponential term will be positive, that is the case for most of the non-degenerate semiconductors, then yeah, am I audible? Hello, am I audible?
Yes, sir.
Okay, yeah, fine. So what I was saying is, because we know that we have a positive exponential term, and similarly in both of these upper formulas we have this exponential as negative exponential. So this is how we came to know that the effective density of states will always be greater than the carrier concentration. This is the case for uh, non-degenerate semiconductors. We need to remember that. And what what do I mean by non-degenerate semiconductor is for a n-type semiconductor, the Fermi level lies always below the conduction band, and for a p-type semiconductor, the Fermi level lies always above the conduction band, always above the valence band. So if uh, give me a moment. Yeah. So if the conduction band or valence band uh, like falls inside the conduction band, then they are, or inside the valence band, then they are termed as degenerate semiconductors. You might have read it in the theoretical lectures, but most of the semiconductors that we will deal are the non-degenerate semiconductors, in which for the n-type we have the conduction band near to the uh, conduction band. We have the Fermi level near to the conduction band for n-type semiconductors, and for p-type semiconductors we have the Fermi level near to the valence band. So these are all the formulas that we already covered in the last lectures. Uh, and then give me a moment. Yeah. So yeah, so we'll be covering most of the degenerate semiconductors that we have. Then we went to the Fermi levels that we had in the last lecture. Give me a moment again. Yeah. So I hope there were no doubts in the previous lecture that we had. So if you have any doubts, you can right away ask. Otherwise, we'll start with the topics that will be covered in this week's only. So if you have any doubt, you can write in the chat box. Otherwise, we'll start with the week 3 questions. So I'll repeat, if you have any doubts from the previous week, you can uh, let me know. Otherwise, we'll start with the week 3 topics. Shall we go ahead with the week 3?
Yes, sir.
Okay, fine.
No doubt, sir.
Okay. So as I said, we'll be covering most of the motions of carrier part. So let me very quickly give you a very brief about the semiconductors that you have already read in the theoretical lectures, but let me give you very quick overview. So if I, let's say, make a periodic table kind of thing. So for the third group, we know that we have boron, then we have aluminium, then we have gallium. Then similarly for the fourth group, we have carbon, silicon, and germanium. And for the fifth group, we have the nitrogen, phosphorus, and arsenic. So these are the most of the group that we are interested in. The first and second groups mostly are metals. Then the sixth and seventh are mostly insulators. And we know that the eighth group is completely noble gases. Yeah. So what we are interested in for the semiconductor range, we are interested in these three groups. So whatever we have, the third group impurities, they are called the acceptor type because they have an extra electron in the valence band. Then these are the donor type impurities, which are group 5. So these type of semiconductor after doping are called as N type impurities. So these are the P type impurities. And the group 4 is giving out the semiconductors. So the most common semiconductor we all know is the silicon that we take as a substrate or the base. Uh, so these are this is the very basic of semiconductors. So if I like classify them into a broad category, then we have semiconductors which are defined as, one is the intrinsic and the second part is a extrinsic semiconductors. Intrinsic is nothing but the pure form of semiconductors. So what we can say that number of holes, if I denote it like this, is equivalent to the number of electrons in the pure form. They are charge neutral. And if I talk about extrinsic semiconductors, then we can have two types, as I said. One is the N type, one is the P type. So if they are doped with a p-type impurity, then they are called as p-type semiconductors, such as boron, aluminum, etc. And if they are doped with the n-type impurities, such as phosphorus, arsenic, etc., then they are called as n-type semiconductors. So this is what we have. And in the previous lecture, we had a question related to the intrinsic semiconductors. Like for intrinsic semiconductors, we know that at absolute zero temperature, we have, if I make it like that, so if we have a conduction band, if we have a valence band, so it is completely filled. So let's say this is EV, this is EC, and this is completely empty. I'm talking about at absolute zero temperature. So what happens is valence bands electrons, they are not capable of taking the energy because we are not applying any temperature, even the thermal motion. So they are not capable of taking energy from the applied electric field, because first of all there are no empty states in the valence band, so there is no motion in the valence band itself, so the electrons cannot move. So there is no contribution of electrons or flow of electrons in the valence band. Then if I talk about uh, the conduction band, so if there would have been any electron in the conduction band, then they are capable of taking the energy from the applied electric field. So the whole motive is only the conduction band electrons contribute in the current flow. So we need to have certain electrons in the conduction band to have a certain current flow. And valence band electrons that we have can only reach the conduction band if we apply a certain energy which is greater than this forbidden energy band gap, that is Eg, that we have. So these are some of the conditions, and at 0 Kelvin we know that there is no thermal energy that is available. So again the valence band remains completely filled and the conduction bands remains completely empty. So that is why we don't have any conduction at 0 Kelvin. And if I now talk about at room temperature, that is at 300 Kelvin, so what we have is number of electron carriers is equals to number of holes, that is equals to the intrinsic carrier concentration. This is a very key thing. So where n is the free electrons concentration, by free I mean that they can move. P is the free hole concentration. I don't need to write free because electron and holes are the moving particles, and Ni is the intrinsic carrier concentration. This is, we all know, I guess, from the basics that are taught in the course by Professor Naresh Imani. And then some of the key things that we have noticed is as we increase the temperature, we have an increase in the intrinsic carrier concentration and we have a decrease in the band gap. So we had certain relations that we have. So I'm just skipping all these n-type and p-type semiconductors, assuming that you already know of these things. So I'll come to the main topic of the lecture, which is a thermal motion or drift or diffusion mechanism. So these all comes under the transport mechanism of electrons. So this is a topic that we will be covering in this week, and we'll be solving the assignment problems related to this. So there are several transport mechanism of electrons, so that we will be covering. One is a thermal, then we have a drift, which is due to the applied electric field, then we have diffusion, which is due to the concentration gradient in the doping. Yeah, so let's start first with the basic topic, which is electric field. So can someone tell what is very basic definition of electric field? Let's say we have a semiconductor, we have applied a voltage, let's say a positive V, and we have a semiconductor of length L. So let's say this is at x equals to 0, this is at x equals to L. So can anyone tell what is electric field in a very layman terms? Any idea? Okay. So if I want to define mathematically what is electric field, it is nothing but the electric field intensity is a rate of change of voltage with respect to the position. So electric field is nothing but dV by dx. So if I talk, let's say in terms of this particular semiconductor bar, let's say we have a zero voltage at x equals to 0, and then we have a V voltage at x equals to L, and then so as I said, at x equals to L we have a 0 because this is 0, and this is, let's say, V here, so L minus 0. So this is what we have as V by L, which is a very basic definition of electric field. And electric field is always directed from high voltage to low voltage. This is what we need to consider, that so if we have a V voltage here, sorry, so if we have a V voltage here, which is some positive voltage, and a ground here, so electric field is always from higher voltage to lower voltage. So this will be the direction of the electric field. So now if I continue, then yeah, so electric field will always exert a force on charge carriers. That is F is equals to QE. We all know this relation very well. So we know that for any electron, Q is negative. So F will become minus QE because Q is negative by default. So the force that we experience by the electrons is always opposite to the electric field. So let's say I have a battery, let's say. So we know that the electron are moving from the negative to the positive terminal. So the direction of electric field will always be like this. Similarly, for holes, if I say, so let's say holes are moving from the positive to the negative electrode. So the electric field is always in the direction of holes. So these are the very basics of electric field. Now, what happens is we have certain velocity of charge carriers. So once we have applied electric field, the carriers move, as we all know. So we have a certain velocity of charge carriers, which we can define in two types. One is the thermal velocity. The second one is the drift velocity. So these are the most important topics for this particular lecture. So please be aware, if you have any doubt in between, you can ask. So thermal, as the name suggests, this is due to the temperature change, and the drift velocity is due to the applied electric field. So let's talk quickly about the thermal velocity, which is the first topic. So we all know that we have, let's say, a semiconductor material. Yeah. So let's say we have a semiconductor material, which is, let's say, a semiconductor which is kept at temperature T, and no electric field is applied. So in this case, electron will have an energy which is equals to 3 by 2 kT. So you all might be aware of this, that in this case we have energy which is equals to 3 by 2 kT. This is the very basic thermal law, which is thermal law of motion. So where K is a Boltzmann constant and T is a temperature, so K have a value of 1.38 times 10 is per 23 joules per Kelvin. So if we have this certain energy, so we know that we only have the kinetic energy component, which is nothing but half mv square. So I'm writing this velocity as thermal velocity, so I'm writing it as Vth. So this will be equals to 3 by 2 kT, and we got the thermal velocity, which is equals to, if I calculate this, it will be 3 kT by m. So this m will be the effective mass, so I'm denoting it with the let's say m star. So we have all the constants, so we can calculate that what is the thermal velocity or what is the thermal limit of any electron that can move. So we have the Boltzmann constant, So I'm calculating at room temperature, which is 300 Kelvin. So I'm taking the exact m naught, which is 9.1 times 10 raised to minus 31. So can someone calculate and give the number quickly? Whatever it will come in meters per second. Uh, so please try to calculate using your calculator and let me know what is the number that you are getting. Okay, yeah. So this is minus 23. I written it plus somehow. So this is minus 23. The Boltzmann constant is 10 is for minus 23. So VTH will something. This is minus 25. Something 10 is for 10. Then I have 9 times from 38 times 9.1. So do you have a number? So if I consider approximately this as 1, so I'll have 10 raised per 5 meter per second. That will give me 10 raised per 7 centimeter per second. So we generally solve all the problems for this semiconductor devices because we have the doping in centimeter cube per centimeter cube. So we generally take all the units in centimeter. So we have the thermal motions and the saturation velocity to that particular thermal motion is 10 raised per 7 centimeter per second, which is at room temperature. So what we can say that the electrons in any semiconductors are therefore moving very rapidly, as you can see, in all the direction, and this thermal motion of any individual electron, if I say, uh, it can be visualized as a succession of let's say various collisions. So let's say I had an electron here, it has moved here, it has moved here, then it has gone somewhere, it has gone somewhere, and it went back here. So this random motion of electron, what it does, it leads to zero displacement. So it is moving so fast that it is leading to a net zero displacement over a sufficient long period of time. So this is what we call as, so this average distance between the collision is called as the mean free path, and the time, the average time between the collision is called as the average collision time or mean free time. So this is all about the thermal velocity of the carriers, which is the first topic. So if I now talk about the drift velocity of charge carriers, which is again the most important topics in the whole course. So if I say drift velocity of carriers. So what we have, as I said, that the drift velocity is due to the electric field. So let's say again I have some voltage. So we know that electric field is the electron motion will be in this side from the negative to the positive. The whole motion will be in this side, and the electric field will be in this direction, opposite to the flow of electron. And inside the semiconductor, we have the electrons flow like this, holes flow like this. So if I like generalize this, let's say I take some lattice in which we have some atom. So let's say electron comes here, it goes somewhere, and it goes like that. And there is always some, due to the thermal, due to some temperature, there will be always jiggling of these electrons. So they are always moving up and down. So there will be some interaction of this electron from this atom, maybe from this atom, and it will go then out. So it will not be a constant acceleration of the electron. So what we have is, on the application of this electric field, let's say electron is moving like this, so electric field will be in this direction. Electron will start to move once we apply this electric field, and this movement is under the electric field is known as drift. This is a very key concept that we are covering. So let's say we have an electron which is in vacuum. Then as soon as we apply the electric field, this electron will experience of or start to move once we apply any electric field if it is in vacuum. But if we have, let's say, a silicon lattice, as I have drawn a very basic silicon lattice, so this movement of electron is not as simple because it will interact with, let's say, the lattice atoms. it will collide with the lattice atoms, and it is very complex to understand this. So, like if I draw quickly, maybe a very basic overview. So, if we have, let's say, some atoms, electron comes, we have applied certain electric field, so it collides with this, it collides with this, and something like that happens. So, we have a certain collision. So, if there is any electric field, the electron never goes through a semiconductor without interacting with these lattice atoms. This is the key thing to notice here. And all these lattice atoms are vibrating due to the thermal energy, as I said. So all of these are like having some motion due to the thermal energy or vibration, and this leads to the scattering of free electrons. Basically they are colliding, and it exchanges momentum. So let's say this is moving like this, and this electron strikes over this, so there is a exchange of momentum, and then again, so what happens is it again decelerates. So once it interact, then it again accelerates due to the applied electric field. So it goes on and on. So there is no constant acceleration, but we have a constant velocity because of this periodic acceleration and deceleration. We have a constant velocity, which is what we call as drift velocity. So this is a key concept that you should be aware of. And what we have is drift velocity of an electron. So if I quickly define what is drift velocity in terms physically, so drift velocity, which is defined by, let's say, Vd, is the velocity acquired by any electron in response to the electric field. So Vd is directly proportional to the electric field. So I've already covered the two most important topics, that are the thermal motion and the drift velocity. So if you have any doubt, you can type in the chat box, or you can open your mic and ask if there is any doubt. Otherwise, we'll move forward quickly. Okay, so I'm assuming that there are no doubts in this particular topic. So let's move ahead. So we have got to know about the electric field, the thermal motion and the drift motion of the carriers that we have. So moving forward, we have, so let's try to solve a very simple question, as I have already demonstrated. So the question says that we have a DC voltage of 10 volts that is applied across a n-type semiconductor, having a cross section of, so let's say we have a rectangular semiconductor having a cross section and length of 1 centimeter. Then we have the donor type impurities, because we have an n-type semiconductor, so I'm writing directly. So Nd is 10 raised to power 16 per centimeter cube, and we have the drift velocity of the electrons, which is given as 1000 centimeter square per volt second. So the average time, uh, you need to find it in microsecond, taken by the electron to move from one end of the bar to other. So you have option 1 TS10, CS100 and DS50. So you need to be attentive here that you need to find the same in microsecond. So I will repeat the question again. Let's say I have a semiconductor bar which is N type, as I've said. It is 1 centimeter in length. It is rectangular cross section, and I have applied a DC voltage of 10 volts. What you need to find? You need to find the average time. So I can give you the hint. We know that time is nothing but we know that speed is equals to distance equals to speed to time. So time is nothing but distance upon speed. So distance that it needs to travel it from one end to other. So this is distance is L, and the speed will be the drift velocity. And drift velocity we have just read it is nothing but the mobility times electric field. So you have everything given in the question. Electric field is nothing but dV by dx minus dV by dx. So we have the electric field given, we have the mobility given. So we'll calculate Vd, we have the L given, and we can find the time easily. So you can take maybe 2-3 minutes to calculate and let me know what is the answer that you are getting. You need to find the answer in microseconds. Again, I'm repeating. So take maybe 2-3 minutes and please confirm on the chat box if you are trying the same. Please write in the chat box yes if you are trying. Any answers? Please type in the chat box if you are trying. Uh, Finally, let me know if you are trying. Otherwise, I'll solve the question. Okay, so let me try to solve it. So this is quite easy. As I said, L is 1 centimeter. So VD we can calculate by mu E. E is nothing but minus dV by dx. So we have a change of 10 volts. So let's say we have a 10 volt here, we have a 0 here. So at x equals to 0, we have a 10 volts. And at x equals to L, that is 1 centimeter, we have a 0 volts. So we can write this as 10 volt per centimeter. So now Vd is nothing but mobility, which is given as 1000, it is given, times 10 volt per centimeter, which will give me 10 raised per 4 centimeter per second, because we have all the units in centimeter till now. And once we have this in centimeter, then we can easily calculate the time, which is L, which is in again 1 centimeter divided by 10 raised per 4 centimeter per seconds. So this will give me 10 raised per minus 4 seconds. That is 100 into 10 raised per minus 6 seconds, which is nothing but 100 microseconds. So the answer will be option C. Is there any doubt in this particular question? Please write in the chat box if there is any doubt in the particular question.
No doubt, sir.
Okay, fine. So let's move forward. We can quickly have a relation for the, since we have already covered the drift part, so we can have a relation for the drift current density then, which is denoted by J drift. So let's say we again have a rod which is applied having a voltage V. Let's say it is length L, cross sectional area A, and let's say this is the cross sectional area, as I said. N is, let's say, number of electrons that we have in conductor. So whatever the free electron concentration that we have is number of electrons, since we have it in per unit volume per centimeter cube. So I am dividing it by the area, cross section area, into length, which is the volume. So this is nothing but the free electron concentration. Then E we already know, for this is V by L. That is the electric field density, again in volt per centimeter I am taking that. And the force that will be experienced, that we have already read, it is nothing but QE. And Q is the charge, which is 1.6 times 10 raised per minus 19. So we know that under steady state, what we have is force is nothing but QE, that is equals to mass into acceleration, from which we will get the acceleration as QE by M. Is there any doubt till here? This is very basic, and we already have this VD as mu E, which on, if you go deeper, then it comes out to be Q tau C. So this mobility is this particular term. If you go to the theoretical lectures, and we already have this solved. So we know that according to Ohm's law, the voltage is directly proportional to I, or I can say V equals to Ri, and where R is rho L by A, where rho is the resistivity, L is the length of the bar, and then A is the cross-sectional area. And similarly, we have a conductivity, which is 1 by rho. 1 by resistivity is given by conductivity. So what I can write is a very basic Ohm's law in terms of So I'm writing R as rho L by A. Then I have a I. So I'm just writing I by A as, so I by A is this particular term, as V by rho L. Or I can write it as 1 by rho into V by L. So this is particular I by A, that is the current per unit area, is nothing but the charge density, which is denoted by J. This 1 by rho is sigma, and this V by L is electric field. So this is the Ohm's law in terms of semiconductors, that we have J as sigma E. I hope this is the current density that we will be solving. So I hope this is quite clear, and this is very basic that we have also read in 10 plus 2. This is the Ohm's law, that J is sigma E. So now I'll calculate the current flowing through the conductor that we have taken initially. So we know that I is nothing but Q by T, or number of electron into the electronic charge by T, and I can write T as L by Vd using the same relation. So I comes out to be N Q Vd by L. Now the charge density that I am calculating is nothing but I by A. So I'm writing this as N Q Vd L A. And we have already calculated or given this term as a free electron concentration, that is N per unit volume, which is given by N QVD. This is the, let's say, some equation. Is there any doubt till here? This is, I guess, very easy and clearly going on. So I hope not. You can ask if you have any doubt. So if I say that the charge density, let's say I'm denoting it by rho V, which is nothing but the charge multiplied by the electron concentration. So by charge density, I mean in coulomb per centimeter cube. So this J comes out to be rho V, that is NQ is rho V times Vd. Let's say this is equation star, this is equation double star. So from equation, this particular equation, we have J as NQVD, and Vd we all know is mu E. So finally, if I relate these, so I can write J as NQ mu NE, and we have just written before that J is nothing but sigma E. So if you compare these two, we will have a sigma of NQ mu N. So this is the what we call as electrical conductivity in metals. So I have solved it for considering single N type. So if I talk about semiconductor, then we have a conductivity which is NQ mu N for the N part and PQ mu P for the holes. So this is the electrical conductivity, and the total J, that is a drift current density, is given by sigma E again. So if I write sigma, so NQ mu N plus PQ mu P E, or even if I take common Q, so N mu N plus P mu P into E. So this is the current density that is due to the drift component. Is there any doubt in this particular derivation? You can ask if you have any doubt in this particular derivation. So if I talk about now extrinsic semiconductors, so let's say I'm talking about N type. We already know for N type, N is very, very greater than P. Since N is approximately equals to ND, and P is nothing but ND by Ni square. So even if I take an example where let's say ND is 10 raised to power, let's say N is 10 raised to power maybe 24 per centimeter cube. So we will have, which is equals to N for N type semiconductor. So we will have a P of 10 raised to power 24. So if I take, let's say, Ni is 10 raised power 10, so this will be 10 raised power 20, which is approximately 10 raised power 4. So P is very, very, very less than N for any N-type semiconductor. So what we will have a J of only the N part, that is N will be equals to Nd Q mu N into E. Similarly for P-type, the second term will be negligible and we will have acceptor ions Q mu P and electric field. So this is some of the basics that we are covering related to the drift current density. So I hope this is all clear. If you have any doubt, you can ask straight away. Please let me know if you are having any doubts. Otherwise, we can solve a question. Shall we proceed?
Can we proceed, sir?
Okay, okay. So try to solve this. This is again a very simple question. I'm not writing much. So let's say we have a N-type silicon bar having Nd given as 10 raised power 16 per centimeter cube. Then we have a DC voltage applied, which is nothing but 1 volt. The length is 1 micrometer of this particular ball. So the first question that I'll frame is, you need to calculate the magnitude of electric field at x equals to 0.5 micrometer. So again, the option will be 1 kilovolt per centimeter, B is 5, C is 10, and D is 26. And the second question for this particular part is, you need to calculate the magnitude of electron drift current density. That what we calculated before, that is nothing but J at x equals to 0.5 micrometer. So I'm writing the options. You can quickly solve the first part till then, which is very easy. So this is 10 raised power 4. All of them has ampere. The unit is ampere per centimeter square. The second is 1.08 times 10 raised power 4. The third is 4.32, and the fourth is 6.48 into 10 raised power 2. All of them has unit as ampere per centimeter square. So this is 10 raised power 3. So please type in the chat box if you are trying, otherwise I'll solve, because we don't have much time to give for each and every question if you are not solving. So please let me know if you are solving in the chat box. Are you solving? Uh, so let me quickly give it a go. So we have just seen that the electric field is constant throughout any semiconductor bar. So for the first part, we'll calculate minus dV by dx. So we know that this will be 0 at 10 raised to power minus 4. So I'm writing everything in centimeter, and this will be 1 volt at 0. That is what we already calculated. So it will give me 1 by 10 raised to power minus 4. that is 10 kilovolt per centimeter. So the answer is C. And once we have the E, we can calculate G easily. So we have, since we have N type, so if I write the complete formula, which is first of all sigma E, sigma is NQ mu N plus PQ mu P times E. So we have already read that N is very, very greater than P. So we can easily neglect this particular term to 0, which will give me a J of NQ mu N E. So we have each and every term with ourselves. N is given as ND, which is 10 is for 16 per centimeter cube. Q is 1.6, 10 is for minus 19. Mu N I have given in the question, or oh, I have not given. So mu N is mobility of electron, which is 1350 centimeter square per volt second. So this is 1350, and electric field we have just calculated as 10 kilovolts. So I'm writing it as 10 into 10 raised to 3. So this will be the electron density in ampere per centimeter square. So if I calculate it quickly, this will be 16 minus 3 plus 3. So this will be 135 times 16, or you can write 1.35 into 1.6 into 10 raised to 3. So something like that. Okay, 1, 2. Okay, so I have 10 raised to 4. Sorry, I have a 10 also. So it will come out to be 1.3 times 2.16 times 10 raised per 4 ampere per centimeter square, which is option A. Please let me know if you have any doubts in this particular question. Is there any doubt? Either type yes or no in the chat box, or you can open your mic and tell.
No doubt, sir.
Okay, fine. So we can maybe go ahead with some of the assignment problems, the similar assignment problems. Uh, so we have a problem in which we say it says that we have a silicon sample maintained at temperature 300 Kelvin. We have a silicon sample. We have an energy band diagram that is illustrated in the figure below. Consider EF as a reference level. So we have a Fermi level which is constant. So if I can make it bolder, so this is the Fermi level. So the question is asking, do the equilibrium conditions prevail, and if they prevail, then why? So we have the option no, because energy bands EC and EV are bending. Then the second option is because energy difference between EC and EI and EI and EV are same. Then the third option is Fermi level EF is constant along X, and the fourth option is EF is not parallel to EC. So do you want to give it a try, or should I explain? Okay, so let me explain. So first of all, you need to be aware that at equilibrium, EF is always constant. This is a way to check whether your semiconductor is in equilibrium or not. So once you can see from the Brane diagram that EF is constant, you can always say that we have the semiconductor is in equilibrium. So the band bending occurs if you have some voltage applied. Let's say if I take this as reference level, so if you apply a certain voltage maybe at one end, so the band will go lower, the EC and EV will go lower, but since the EF is constant, you can always say the electron is in sorry, the semiconductor is in equilibrium. So because EC and EV are bending, that does not mean that it is not in equilibrium. The main thing is EF should be constant. So option C will be correct to this. It will be in equilibrium because the Fermi level EF is constant along the given position. Sorry. So along X we have EF as constant. So implies equilibrium condition. So option C is correct. Any doubts? Okay, so I hope there is no doubts. We can move forward. So you can give it a try. This is a very basic question. I guess this is this year's assignment problem. So you can give it a try and I'll give you 2 minutes. You can type your answers in the chat box. This is ABCD. Take 2 minutes and give your answer. Okay, is anywhere ever aware about the Einstein relation? You can open your mic and tell. So I'm assuming you're not. So according to Einstein relation, what we have is the diffusion constant dn is equals to mu n kt by q. That is, we can write dn by mu n is kt by q. Kt by q is nothing but the thermal voltage, which is also denoted as Vt. And for p type, we have similarly mu p by k, mu p kt by q, or dp by mu p is equals to kt by q, which is again the thermal constant. So we can write the Einstein relation is dn is equals to dn by mu n is equals to dp by mu p is equals to kt by q. So I'll write where k is the Boltzmann constant again, q is the charge, electronic charge, and T is the temperature. So we all know at room temperature at 300 Kelvin, this kT by Q is nothing but 26 milli electron volts. So the option 1 says it depends upon the type of semiconductor, so it is wrong. The ratio of this diffusion constant to the mobility is only dependent upon the Vt for both the cases, if it is a N type or P type. Then it varies with the lifetime of the semiconductor, so it is also wrong. It is only dependent upon the Vt, which is only temperature dependent. It is not constant, it is varying with temperature. And the last option is it depends upon the temperature. So yeah, option D is the correct answer. Is it clear? This is quite easy, I guess. So please let me know if it is clear so that we can move forward. Then we have certain more relations. Maybe I can write here only. Then we have diffusion length relation, which is for N type. It is given by dn times tau, where tau is the lifetime. Dn is a diffusion constant again. I should write in general. So this is calculated for minority carriers. And L is the diffusion length. So again we have a D, which is mu times kT by Q, that we all know already. And the diffusion length is given by this particular relation, which is under root diffusion constant times the minority carrier's lifetime. So is this particular thing clear? Please type yes or no in the chat box quickly. Is this particular thing clear? Kindly write yes or no in the chat box. Is it
Sir,
clear?
please repeat again.
Sorry, should I repeat?
Yes, sir.
Okay, okay. So we have diffusion length, which is given out by the relation under root diffusion constant times the lifetime. So what I said is we need to calculate it for the minority carrier. So the diffusion length L is always calculated for minority carriers. So let's say we have N type semiconductor, and which is given, let's say it has certain mobility, so it will have certain diffusion constant dn, because we have N type semiconductor. But the time period that we will take, or the lifetime time period that we will take, is of always of minority carriers. So we should take tau p, you can say, because it is a N type semiconductor, so the calculation will be done using the minority carrier's lifetime. So this tau is a lifetime for minority carrier. This is the main thing that you need to know. Is it clear now? Please let me know if this is clear. Uh, is it clear? Am I audible, everyone? Hello.
Audible, sir.
Okay, so if it is clear, then you can solve this question. This is very easy. It is just formula based. So it says the mobility of the minority carriers already given for a n-type semiconductor is mu p. Because of n-type, the minority carriers will be holes. What is the diffusion length is the question. Assuming the minority carrier lifetime is given as 10 microsecond. So this is direct formula based. So we will have a dp times tau p. dp is we have just related with the Einstein relation, which is mu p by kt by q and tau p. Everything is known to us, so the temperature that we have it as at room temperature. So kt by q is 26 milli electron volts you can take, and let me know what is the length that you are getting. So mu p is given as 480. Then we have 26 times 10 raised to power minus 3. So this is in electron volts. This is in centimeter square per volt second. So we need to divide it by, I guess, tau p is 10 microseconds. Yeah, just let me know what is the value that you are getting. Any answers? Please let me know if you have got any answers. So what I'm getting is 1.117 into 10 raised to power minus 2 centimeter. So if I write maybe here, so this will be 111.7 into 10 raised to power minus 4 centimeter, and this is nothing but micrometer. So the answer will be 111.7 micrometer. That is option C, the closest option. Are you also getting the same? Please confirm if you are getting the same answer. Could you please confirm? Did you try? Okay, so I'm assuming that you tried. So now this is a good question. So it says we have a sample of semiconductor which is having a cross-sectional area of 1 centimeter square, a thickness of zero point 0.1 centimeter. The number of electron hole pairs that are generated per unit volume per unit time by a power absorbed of 1 watt and wavelength 630 nanometer. What is the approximate steady state excess? So steady state excess carrier concentration is denoted by delta n if you have read the theoretical lectures. If the excess minority carrier's lifetime. So the minority carrier lifetime is again given as 10 microseconds. Assume each photons create one electron pair. So this is again a very easy question. So we know the wavelength and we will calculate the energy first, which is hc by lambda, which is in joule, and if I write the shortcut, it is something 1.12 times, or I guess it is 1.24 times lambda in micrometer electron volt. So it is already given in nanometer. So this is 1.24 times 0.63 in micrometer electron volt, which will come around 1.97 electron volts. So wavelength of 630 nanometers corresponds to 1.97 electron volts of energy. So once we have the energy, this is direct. So the number of, first of all, will calculate the number of generated carriers, which is energy 1 by energy. So I'm calculating this in joule. So I'm multiplying it by 1.6, the charge that we have per unit volume. So the volume we need to calculate, it is given as point. So this is volume is area into length, which is 1 into zero point 0.1, which is zero point 0.1 centimeter cube. So I'm writing zero point 0.1. Sorry, we need to divide because it is per unit volume. So if you calculate this is 10 raised to the minus 20. The unit for this particular thing will be per centimeter cube per second. So if I calculate this will come around 3.17 10 is to 19 per centimeter cube per second. So now what we need to find out? We need to find out the steady state excess carrier concentration. So we have some lifetime. So we already know that the total concentration is given out by the generation is given out by the excess concentration divided by the tau. So delta n we need to calculate, which is equals to g times tau. So this is a good question because we have both the g and I guess delta n in the option. So one might be thinking that this is the correct answer, but this is not correct because ultimately we need to find out per centimeter cube, that is the excess carrier concentration. So that will be 3.917 10 raised to 19 times the minority carrier lifetime, which is given as 10 microsecond. So it is 10 into 10 raised to minus 4 centimeter, and the unit will be per centimeter cube. So this is 20 minus 4 is 16. Okay, I've written something wrong. 10 microsecond is 10 into 10 is to minus 4 centimeter. Okay. 10 micro, not seconds. This is 10 raised to minus 5 seconds. I need to calculate seconds. I was changing it wrong. So this is 10 raised to 14 per centimeter cube, which is the excess carrier concentration, which is some option, which is option C. Is there any doubt in this particular question? Please let me know if you are having any doubts. Okay. So if there are no doubts, you can calculate this. We have already done this in the initial part of the lecture while I was explaining the theory. So you need to calculate the thermal velocity. So I'll give you the hint that the energy due to the thermal velocity is 3 by 2 kT. So you need to calculate the approximate thermal velocity of electron and holes. So you can calculate for electrons giving the effective mass as 0.26 m naught. We have already calculated it in the initial part of the lecture. So already the unit is given. You need to find this particular value. Quickly let me know this. You can take 2-3 minutes and please let me know if you are solving. Please type in the chat box. This is very easy question. I guess you can solve this. Kindly type in the chat box if you are solving it. Please respond, guys. Am I audible? Please respond if I'm audible. Hello. So we have half mvth square as 3 by 2 kt.
Audible, sir.
So the vth will be 3 kt by the effective mass. We have everything with us. 3 times the Boltzmann constant, which is minus 23. Then we have room temperature, which is given 300. And at last we have the effective mass, which is given as 0.26 times of m naught, which is 9.1 10 raised by minus 31. So if you calculate this, it will come out to be some number. Please give me this number, which is either option A, B, C, or D. Please let me know if you are solving quickly. Okay, so let me solve. So this is 3, is around 4, it's around 12, 48, 9. So this will something come 2.3. So I'm assuming this will come out to be 2.3. So option C is the correct answer. Let's move ahead. So we have another similar question which in which we calculate the whole diffusion length. So we have a, let's say it is given that we have a very long p-type silicon bar. So p-type means minority carriers will be n-type. So Na is given as 10 raised to 17 per centimeter cube. We have a area of 0.5 centimeter square. The steady state excess hole concentration. So we already have the steady state excess hole concentration, which is 5 times 10 raised to 16 at x equals to 0. Mu p is given 500 centimeter square per volt second. Kt by q is 26 millivolts. Tau p is also given 10 raised to minus 10 seconds. This is quite easy. We don't even need all this information because we just need to find out the diffusion length, which is nothing but under root dp tau p. Dp is mu p kt by q times tau p, and everything is given. Mu p is 500, which is in centimeters. So 26 10 is for minus 3 volts, then tau p is 10 is for minus 10 seconds. So we need to calculate the same in micrometer. So let me calculate minus 13 minus 11, which is a 30, 13. So this is 10 is for minus 5 and root 30 into 10 is for minus 5 centimeter. So what is under root 13? I need to check. Okay, so we have 3.6 into 10 is for minus 5 centimeter, or we can say 0.36 into 10 is for 4, that is micrometer. So we have the diffusion length as 0.36 micrometers. So option B is the correct answer. I hope it is clear. This is very easy. So let's move ahead to the next question. So now we have a n-type semiconductor which is given with a
Sir, screen
non-uniform.
does not show.
Sorry,
Screen does not show, sir.
I don't understand. What are you saying?
Sir, answer does not show, sir.
Answer is
Not showing, sir.
answer is not correct. You are saying.
No, no, sir, not showing. It's not showing, sir.
You can type in the chat box. I'm not able to understand what exactly you are saying.
Okay, sir, I can see.
Okay, is it fine?
Okay, sir.
Okay, fine, fine. So now we have an n-type semiconductor which is given with a non-uniform doping now, which is given as 10 is per 16 exponential of minus x by L, where L is 200 micrometer and temperature is 300 Kelvin. We need to find out the induced electric field, which is in volt per centimeter, for a semiconductor at x equals to 100 micrometer. So we have a direct relation for this, which is minus kT by q times 1 by nd dnd by dx. This is already taught in the lectures, so you can give it a go. I'll solve it quickly. So E is minus kT by q 1 by nd times d by dx of the given nd, which is 10 raised to 16 exponential of minus x by L. So if I take the differentiation of this is 1 by nd, then again 10 raised to 16 is constant, exponential minus x by L, and minus 1 by L will come out because of the differentiation. So if I write everything now, so nd is already given, which is 10 raised to 16 exponential minus x by L times 10 raised to 16 exponential minus x by L into minus 1 by L. So this will get cancelled. What we are left with is kT by q times 1 by L. kT by q is 26 millivolts, which is given at room temperature, we already know, and 1 by L is, so we need to find this at x equals to 100, but we are not worried about that because we need to find it at so length is given as 200 micrometer. 200 micrometer means 10 raised to minus 4 centimeter, which is 2 into 10 raised to minus 2 centimeter. Then This is minus. So we have 26 times 10 raised to the minus 3. This is 10 raised to the minus 1, 13. So 1.3 volt per centimeter, which is option B. Is it clear?
Got it, sir.
Yeah. So we also have a similar question, I guess, in this week's this particular assignment, which you can solve by yourself. I guess all the values are almost same. So we have a donor concentration in an n-type semiconductor given. Again at room temperature, so Kt by Q will be 26 millivolts. Nd is the exact same that I have calculated in the previous question. So this is again 200 micrometer length and X is 100 micrometer. So the question is exactly same. You will get the same answer. Is it fine?
Yes,
Sure.
sir. It will be done, sir.
Sorry.
It will be done, sir.
Yeah, yeah. So I'll not solve it again. So let's move ahead. So okay. So we have a Venn diagram given in the question. So the question says at the position x1, what is the type of semiconductor? So x1 is this particular position. Let me darken it out. So you can quickly tell what is the position because this is very easy. I hope you already know. So let's say we have a EC, we have a EV, we have some intrinsic level EI. So this is a very basic level question. If if the Fermi level is close to the conduction band, then we have a n-type semiconductor. Similarly, if a Fermi level is close to the valence band, then we have a p-type semiconductor. So we can see in this particular region, that is at x2, if we consider this as EI, so the Fermi level is close to the conduction band. So this is a n-type semiconductor. At x1, this is a n-type semiconductor. So at x2, can you quickly tell what is the type of semiconductor at x2? So this is x2. Please quickly let me know. This is very easy.
P-type, P-type, sir.
Yeah, so it will be p type, and it is very close to, you can say, the for valence band. So you can even say p plus type, that is very much highly doped p type semiconductor. And similarly here, if I draw a line, so it will again be p type. So this is n type and this is p plus type, you can say. So I hope this is clear. So let's move forward. Okay, so we have another question which is quite a good question, I guess. So we have a long rectangular bar of direct band gap p-type semiconductor. So we have a p-type semiconductor, which means we have given Na. Na is given by, it is given. Yeah, the Na is given by 10 raised to power 17 per centimeter cube. We have the intrinsic carrier concentration given by 10 raised to power 10 per centimeter cube. Then the electrons and hole diffusion length. So Ln is 2 micrometer, Lp is 1 micrometer. The left side of the bar, so at x equals to 0, the excess electron pairs generated only at x equals to 0 because of the laser. The steady state electron density, so if I write at a steady state, that is delta n at x equals to 0, it is given by 10 raised to power 14 per centimeter cube due to laser illumination. So under these conditions and ignoring the electric field, so there is no electric field, the closest approximation of the steady state electron. So again we need to find the delta n at x equals to 2 micrometer. So this is the question. We have everything given in the question, we just need to find out the delta n. So this is again straightforward. We know that delta n is nothing but delta n at x equals to 0, that is at x times e raised to power minus x by ln. This is already taught like in the directly in the theoretical lectures. You can take a reference from that. So delta n will be 10 raised to power 14, that is already given, exponential of minus x. So x is given as 2 micrometer and ln is also given as 2 micrometer. So it is nothing but 10 raised to power 14 times exponential of minus 1. And exponential of minus 1 is 1 by e, which is given out by 0.37 10 raised to power 14. And in general, if you go to the very correct formula of NP, that is in the P type, what is the excess minority carrier concentration? This is given by NP naught plus delta N. This NP naught is nothing but the equilibrium condition, which is, you can also call it as ND approximately, which is Na by Ni square. So this is already given in the question, which is 10 raised to the power 17 by Ni square is 10 raised to the power 20, if I'm not wrong. Yeah, which will give me 10 raised to the power 20. Sorry. So this will be Ni square by Na. So this is 10 raised to the power 20 by 17. So NP naught will come out to be 10 raised to the power 3 per centimeter cube, which is very less as compared to the second term, which is 0.37 times 10 raised to the power 40. So I can write this as 3.7 times 10 raised to the power 13 per centimeter cube, which is nothing but the excess carrier concentration at x equals to 2 micrometer, which is asked in the question. So the answer will be 3.7 10 raised to the 30. So option A. Is it clear?
Okay, sir.
Okay, fine. So as I can see, like a lesser number of students are joining the live session. So is there some particular reason? Are you all finding the course difficult, or you're not able to grab whatever is taught in the live sessions? Can you provide your feedback for the same? Uh, you can also type in the chat box if you're shy
So
to.
it is just bit complicated. Like it's getting so many terms and like to grab all this at once. So
Yeah, so that is why I am covering each and every points in the initial part of the lecture and then solving the question. So as you can say, today I have all first covered all the very basic terms so that you can get the idea of what is the meaning of each and everything, like thermal velocity, drift velocity, electric field, what is that, and then I went to the problem. So that way we can get a better overview of the course. So as you can see, I've even go towards the semiconductors. What are these? What are the extrinsic type? Why do we call it extrinsic? Then what are the band diagrams and all? So you will get to know, or even if you are still having problem in getting these very basic terms, you can always mail me. Maybe what we can do is we can make a WhatsApp group of all the students, and you can add me in that group so that it will help. So
sir, not
yeah,
able to hear you, sir.
am I not audible? Hello, am I audible? Please, someone confirm.
Audible, sir.
Okay, so can any of you make a WhatsApp group and for all the students and add me in that group so that we can have maybe interaction in that group so that the number of participants will be more and also we can have more easy way of solving the problems.
Yes, sir. Just can you repeat? I was not able to hear. So
So okay, so what I was saying is maybe we can make a WhatsApp group in which we can interact with the very basic problems that you all are having, and that group will also help
Yes,
in
sir.
sorry.
Yes, sir. WhatsApp group
Yeah,
can help.
so I hope you all of the students have access to each other, like the contacts are there in between the students. So maybe you can add me in that group. So I'll share my contact. Maybe let me pause the recording first.
Sir, I can get mail.